Is about 2 weeks old, and the large cell running diagonally across the field is approximately 20 microns across in the middle. We're going to bring the patch pipette down on top of the cell, just enough to dimple it. This will raise the resistance of the patch pipette by a factor of 2. Then we're going to go take a look at the electrical counterpart of this. This is a calibration signal showing a 5 megohm pipette resistance. Now the pipette is going to be pushed up against the muscle cell, cutting the current in half. Now suction is going to be applied. In this case, suction by mouth, there. Suction is just held a little bit, there. That's a gigaseal. Turn up the gain, there are the channels. That's it, that's all you have to do. At this time, the easy part has been done. It's easy to obtain single channel data. What's hard, and where the grind really begins, is to reduce that data to some meaningful form. The most important part of data analysis is taking a good look at the data. Now, if we take a look at some raw data plotted out by the computer, we can take a look at a few things. This is the baseline level. This happens to be a single channel record from stretch activated channels. Here's the baseline. Here's an opening, closing, stays closed, opens, closed, and so on. The data appears as bursts of activity. The computer has underlined those bursts which it has identified. This particular program is rather robust and isn't easily fooled by noise and seal breakdown and that sort of thing. What information is in this record? Well, number one, we can look at the amplitude of the channels. We can, two, look at the durations of events. We can look at the open times, we can look at the closed times. The problem with single channel data is that the durations are distributed as an exponential random variable, which means that the mean of the distribution equals the standard deviation. So to reduce the uncertainty, for example, in a lifetime requires collection and analysis of a lot of events. You've got to reduce the standard deviation to a standard error of the mean. This typically means analyzing data that contain upwards of 500 events. To separate two exponentials, you're going to need something on the order of 5,000 events for accuracy. Let's take a look at some of these analyses. This is the on times. This is a linear plot of the number of counts versus time. And these are 100 microsecond bins. There's a roughly exponential decay. The number of components in this decay is an indication of the number of open states. Similarly for closed states. If there are two components, there are two closed states, provided that there is actually only a single channel present. If there's more than one channel present, the conclusions are not nearly so simple. Here's a plot of the closed times. Again, at 100 microsecond increments. At this time scale, it's roughly a single exponential. There's a plot here with a 10 millisecond time, and there are very few counts that are visible at that time scale. On the longest time scale where we have, somewhat mislabeled, 10 milliseconds per bin, you can see another exponential component. In the case of the stretch-activated channel, it's this time constant which is regulated by membrane tension. If we take a look at the burst length, that forms a fairly simple histogram, approximately single exponential. The number of events in a burst is plotted over here. It's a rather scattered plot, but it roughly follows a geometric distribution, and the combination of this, the open time, the closed time, and the burst length can often be used to derive kinetic parameters for a model. The amplitude information can be examined in a couple of different ways. This is a raw amplitude histogram of the data after correction for baseline offsets. This actually represents zero current. And you get a big peak indicating that the channel spent most of its time at baseline. This peak occurs at an amplitude equal to the single channel current. There's almost an invisible amount of extra activity in this record. This plot is a maximum likelihood estimate of the number of channels present. Its maximum occurs between 0 and 4 and approximately 2, indicating that the most likely number of channels in that patch of membrane was 2. Should be aware that such an estimate is only valid if the data is stationary and represents the activity of identical channels. There are other ways to examine the data. This is a plot of the average leading edge of a burst. During this time, the channel was only measured if it was closed for this period. Then they were aligned on the leading edge, and they were required to be open for a certain period of time. Current very cleanly jumps from 0 to maximum, but then decays to the average current level during a burst. The clean jump indicates that there are no substates which are unresolved occurring during the leading phase. We can make a similar analysis for the closure of bursts. We can do the same analysis for gaps within bursts. This is a plot of the amplitude distribution of all points selected to be within bursts, which is sometimes a help in looking at multiple conductance states within bursts. Now, what you see depends upon how you analyze the data. If we take a look at the total amplitude histogram here, you see a rather smooth curve. This is actually a histogram of all of those points that are below threshold. If we calculate instead of all points, calculate the average amplitude of all points below threshold, you get this curve, which is narrower but has a little bit of a peak right over there. If we plot that same data as a cross-correlation plot of the average open time versus the average amplitude, it becomes much clearer. Here is the close time in 100 microsecond units, and here is the amplitude. You can see that there are two distinct populations here, two different amplitudes, and to the practiced eye, this one has a longer time constant than this one. This is a plot of activity from a calcium-activated potassium channel. If you were to look at this data, it looks rather pretty, lots of activity. And if you made histograms of this activity, you could get useful data out of it. The problem is, in making a histogram out of the entire record, you have to be assured that this is representative of the entire record. One output that we found very useful is a measure of data stationarity. This plot shows the average channel current as a function of time through the record. It's been averaged over about 1,000 points. Each data point in this plot is the average current over 1,000 data points from the other one. So it's a very low frequency version of that data. As you can see, there is a substantial variation in the mean current from the beginning to the end of the record. The record runs this way. In fact, you see bursts that occur on a time scale that's 1,000 times slower than the original data record. This says that if you lumped all those kinetics together, you would get a very confusing answer. Beware. Here's another example of a lack of stationarity. In this case, this was an acetylcholine activated nicotinic channel. At the beginning of the record, there's a lot of activity, and as time goes on, the activity drops off and drops off and drops off. Again, if you take the kinetic and duration on and off data, you lump it together into a histogram and try to fit it, you're going to get a very confusing answer, because the kinetics here are not the same as the kinetics here. It's not simply due to a loss of the number of channels. There are real kinetic changes taking place. The only time the histograms are valid is when you can show that your measure, whether it be on times, off times, probabilities, amplitudes, or whatever, is constant from the beginning of the record to the end of the record. In this record, this might be considered a reasonable measure of stationarity. This is a stretch-activated channel, and most forms of activity seem to come and go a number of times before the record is over. This we would regard as a fairly stationary piece of data. For development of automated analysis, measuring all these properties of ion channels was a real chore. We've now been able to simplify the entire analysis procedure so that we no longer have to do any hands-on analysis. We just turn it over to the computer.